Hello, we are back to continue our this time is script number 28. Okay, it will be the conclusion of the part of LP with too many constraints and too many variable. But now we will consider coding the idea in these two slides. Okay, of LP with too many rows and too many columns using what we call the Matlab environment as you show here. Okay, I'm gonna explain a little bit. Okay, I hope that you're familiar with the Excel platform from the previous two clips. Okay, and we're gonna start with the file we call LP solving M. Okay, there are actually three files in MATLAB that I want you to take a look here, and all of them is all included in the lecture 3 folder here. Okay, there will be the LP direct solving and LP with too many constraints or rows, and LP with too many constraints and column. Okay, and there will be some additional one more program about the big data metric storage we will discuss at the end. Okay, let's now go back to the MATLAB environment. Start with the what we call the file, the program called LP direct solving.m. Okay, this is just a basic code for to generate an LP problem, and then you solve it using the linproc, the direct linproc software. Okay, we'll start with certainly the first statement is clear the number where all the variable, and then we start tick and talk here to try to this one is from line 2 and line 18. Okay, we're trying to measure all the processing time to generate the problem, and then we count the time again just for the execution of the linproc object. Okay, so the first part from line 3 to line 17 is the way that we randomly generate the problem. Okay, and the way we're gonna solve the problem down here, it will be a kind of uh, the inequalities type of problem. Okay, because this one we have no equation involved here, and mainly all the lower bound is 0. Okay, and then in this routine from line 9 to line 14 is how we randomly generated the coefficient of a sub I j and the right hand side of b sub I. Okay, certainly the right hand side b sub I is a rounding for the integer of be using a random number generator time 101 and plus 300. So we start with around 300 and end up at most is should be around 401. Okay, and for the a sub I j, okay, a in row I column j is just direct the integer value have at least the one value. Okay, and then with the 2-digit of rounding. Okay, with the random number, so it will be all between 1 to 2. Okay, with two precise digit. Okay, for aij and cj. Certainly we use the minus sign. Okay, we use the minus sign here because the default of the inequalities, okay, for linproc is always less than or equal. When it's all less than or equal, okay, you don't want all the c to be coefficient to be the positive value, because with the positive value is one the obvious for the minimization problem is that you use all the lower bound of x. If you assume x is all equal to 0 with all positive coefficient of a sub I j and the positive right hand side b. The trivial solution is that x is equal to 0 imply the minimum value. Okay, so we're gonna generate c as a minus sign. Okay, so to make it maybe if you reverse the sign of C, it's become the maximum problem. Okay, certainly we round the number with 3-digit accuracy and with minimum value of 0.1. Okay, and this is the way that we directly solve the problem. This one we randomly generate what we call the 100,000 problem with the number of variable of 10. Okay, we might start with 10,000 first. Okay, and this one you have 10,000 variable with 10 decision variable, all inequalities, okay, of ax less than or equal to b, and with all the randomly generated of c parameter and a matrix and c vector and b vectors. Okay, we should be able to run this one. Okay, so we're going to run this. Okay, and then we're going to take a look at command effort. Okay, it's shown down here. Okay, here elapsed time is 1.9930 within 2 seconds. Very fast, huh? Very fast also. Okay, but I want to show you this number first. Okay, this one we execute LP solving. Okay, the two elapsed time and optimum solution found down here, and elapsed time of 169.495 seconds. This one is the I did run it before. Okay, while I'm using this program, but at that time m is equal to 10,000. Remember that I erased 1 0 here. Okay, so this is the computing time. I'm not going to rerun it again because it took maybe 2 minutes or something. We don't want to wait it. Okay, the elapsed time first. Okay, is the time measuring how to generate a problem. Only 0.574. Okay, 583 seconds. And then the optimal solution found, okay, at the elapsed time of around 2 minutes, almost 3 minutes. Okay, 169.495135. Okay, this one is we execute. I did execute it before. Okay, so you know, you can see that if I keep increasing the m, or either I fix a small m and we imply very large n. Okay, the response of the, think about it, if we add one more 10 times more of m to become 100 a million constraint. Okay, certainly the time over here will take maybe 10 times. Let's just guess 10 times more. 10 times more is become almost 1,700 seconds. 1,700 seconds divided by 60 seconds. Okay, it took almost half an hour. Okay, and but you cannot just keep approximate that. You can add this. Okay, add this 0 and then just run it. Okay, and you will see the response. Okay, but you start to know that if you keep increasing this, it's going to cause you some problem. Okay, that's why we develop what the routine called the LP with too many row. Okay, too many constraint or row. This one. Okay, this one we implement using similar. Okay, this one is from line 12. It's highly similar to what we have used in the file of LP direct solving. Okay, but we separate 2m. The capital M is a total number of constraints. Okay, this one we give you a million constraint, right? You can see that this one a million constraint, and initially we start with 50 constraint out of million constraint. With the number decision variable is 10. Okay, so the LP with too many constraint or row. Okay, we are using what the idea proposed in this slide. Okay, because when n is much more than m, we use a prime as m times p. Okay, this one too many variables. Sorry, you have to go too many constraints. When m is, we use approximate a pi p times n. In this case, m is very large, or like million, and then we only use 50. Okay, and you can go back and check the logic of the program. Therefore, Your A full is the full model, okay? You have M constraint. But this one you have A sub with only M. Okay, and certainly we reserve the space for B, all the right hand side, the capital M, okay, amount of capital M. And C only N variable, and L is only N variable, small value. Okay, certainly B sub is only small m, okay. Okay, and then you can see here that we generate, okay, the first part we generate the full matrix of A, okay, and then we only took the first M constraint instead of, okay, instead of using all the capital M to move some data from A full, okay, A full matrix, okay, to A sub for only M constraint, or M rows, okay, and certainly Cj, okay, we need to use minus, and also with decomposition of a row, okay, number of row, okay, so we also have a subvector of B sub I equal to Bi for only I equal 1 to M, not a small m, not the capital M, okay. That's and then we stop down here the command stop to measure the time, okay, from line 2 to line 29. First of all, they will measure the time, okay, for the problem setup, okay, both randomly generated and allocation to a small metric. So the key part of the row gen program start with row 30, start with 30 start to count the time, but the logically start at line 31 here in the program with a very small loop here, okay. We will try to look at here, okay, since this is the minimization problem, okay, we check the minimum of RC mean RC mean reduced cost coefficient. Initially we set it to be a highly negative value, okay. Why we want the negative value? Because if all reduced cost coefficient is a negative value, therefore you are at the you cannot you are at the top of the objective function, okay, the peak of your objective function, okay. So we start with a minus a very large value first, and then ITR is counting the number of iteration, okay. So we check whether you still have a negative minimum reduced cost coefficient, okay. Remember that if you still have the reduced cost coefficient less than 0, okay, it means that your solution is not reaching the optimum solution yet, okay. But you might don't confuse with the case of too many variables, okay. I'm using the same reduced cost coefficient here, but in case of when you have so many number of constraints, okay, the reduced cost here, okay, computed from right hand side the vector b minus a full times x, which means the full matrix of A, okay, times x, b minus ax. According to the constraint here, okay, we're working on the A sub, B sub, okay, A sub less than or equal to B sub, okay. So we are using the right hand side minus the left hand side, okay. And the reason is that if all are feasible, the RCC should be greater than or equal to 0, right? Because it's AX should be less than or equal to B, okay. And you might wonder why we call this RCC. This should be the difference between the left hand side and right hand side. Actually, it's the reduced cost coefficient of the dual variable, okay, for this primal model, okay. And so that's why I use the same name, okay, and terminology to the LP with too many column also. So what I mean here, the reduced cost here, this one is the reduced cost for the dual variable according to the constraint that haven't been added to the original problem yet, okay. So at first we it's gonna get into the loop immediately because we start with min r with min rc with the negative value, and we didn't use the zero value, right? You might use min rc less than 0 or something, and I use just minus 0.01. This is due to the as you all know, when you're using the computer to compute the number, okay, they always have some round off error, okay, because of the irrational number operation, okay, in the computers, okay. So this one is kind of, we try to make sure that the accuracy of the first 4 digits of the results can be achieved, okay. So if there will be any mistake, and possibly it start at digit number 5, okay. So this is the way to it's kind of tricky, okay, when you're dealing with computer that's not perfect for computation of number, okay, because they only compute the number with the irrational number that have to be controlled by the number of bit and byte that represent the number, okay. So you can never get all the exact solution, okay, and you can only have some approximated up to which number of digits that you are interested in, okay. So ITR start counting, iteration start counting, and then we start solving first, okay. And I'm using actually for LP with too many constraints. Sometimes I really don't need the other 3 like exit flag, output, and lambda over here, okay, because we don't need any dual variable here, okay. Lambda here is an attribute that give you the dual variable, okay. In Matlab we use lambda instead of dual variable to say there is a dual variable, okay. So you should know that when you add this parameter, you want the Excel to return this object, not only the x value or the objective function, okay. You want to show the dual solution, so also in the vector of lambda, okay. And they start solving the problem, start with C and A sub and B sub as inequalities. Once you get the solution X here, okay, you go find the difference between left hand side and the right hand side using the full matrix of A, okay. And now you are checking here, this is a additional statement here, okay. You want to find the minimum of RCC. RCC is a vector, resulting vector, okay, of the right hand side minus the left hand side. You want to pick the minimum value. The minimum value is the one that maybe the most negative, or if possible is still greater than or equal to 0, okay. Because if it's greater than or equal to 0, it's terminate, okay, because this do while loop, okay, have to be terminated. But if you still have a negative value, right, which means that there exists some constraint that is infeasible, right, because if it's negative, it means that B is less than A times X, okay, which is not the constraint you decide here based on the default of the linproc procedure, okay. So the command here, the min RC index, will help you to the index will help you to identify that which element in RCC, okay, that achieve the minimum value, okay. Once you know the index, okay, so you can be able to identify the new row of A news, okay, from the A full, okay, of index, okay. Since this is a low index row, okay, and all contain all the column here, comma, and then column here. So all data in the A matrix of row index, okay, row number in index, and all the data, okay, will be put in A news as a row vector, okay. And the right hand side vector B new is certainly B as the index, okay. And for the Matlab program, it's very easy that I just update the A sub and B sub by using CAT command. CAT command is a kind of additional, when you have additional row or column, okay, you want to add into the matrix of vector, okay. So this one, okay, A sub is equal to cat. Okay, 1 is a parameter that you want to add at the row. Okay, so it means that the new a sub, okay, you add a new row called a news down here, and the right hand side b subs, okay, you add one more, okay, from the original b sub with b news. Okay, and a new b news, okay, is belong to the same location element in the both vector and the metric where they belong. Okay, and then after that, okay, m is equal to m plus 1. Remember small m, because small m is a initial value of the number of constraints that you put into your consideration for when you first solving the linear program. And then if this mean RC, if there's still violation, okay, that there exists that b is less than a times x, okay, they'll pick the minimum one and keep adding the new row, okay, as a new and b, and resolve this command of linproc again and again until the minimum RCC, okay, that the minimum of this RCC vector that will be put in the min RC based on this command. Okay, if the minimum value is still start greater than or equal to minus 0.001, which means that it start getting all the not become the minimum value become the non-negative value. Okay, when you know that all the reduced cost coefficients are the minimum value is become the positive value, so with the minimum reduced cost coefficient is have to be greater than or equal to 0, which in over here is satisfy all the constraints, right? RCC, because RCC is the left hand side minus the right hand side. Again, I would like to say that I call this in both program that I will show you later about the column gen and row gen, because in row generation RCC is a difference between the left hand side and the right hand side, but actually it's a reduced cost coefficient for the dual model of this too many constraint problem. Okay, so it keep do as a loop here until you found that all the constraint has been satisfied, which means that b minus a times x are all greater than or equal to 0. If it's happened in that iteration, you mean the last solution of x imply with f wow as the objective function imply the optimum solution for the whole process. Okay, so that's the logic of LP with too many rows. But I'll give you this example that, okay, we solve this problem with 10 million variable. Okay, but this one is 1 million already, right? Okay, I'm going to add one more. Okay, suppose that I have 10 million variable here. Start with this. Okay, 10 million variable, and I can run it again for you, but to check it out. But actually, I did run it first already here. Okay, you see that this is the execution of the file of the run of the program running of LP to many variable. Okay, too many constraints with low generation. Okay, I missed 1 0 here. one double O. Okay, I put only 1 O here. Okay, the first elapsed time is 5 seconds. Is the time that you initiate the problem. Okay, and then in this case, the problem didn't take very long. Only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Only 10. We add only 10 constraints and took only 8 seconds. Okay, that the optimal solution has been detected. Okay, and with LP with too many variables we will discuss later, but that's okay. Okay, since we already add up this problem, okay, we're gonna try to run it after this one. Okay, so this problem is become you can see there is a 10 million constraint, okay, with only 10 variables. Okay, you remember that in our LP direct solving, the same situation with 10 decision variable, but only 100,000 constraints. Okay, but with this row generation, we add it up to 10 million constraint. Okay, with 10 decision variable. Okay, I'm gonna run this program, okay, and see the response down here. Okay, so you have to wait until all the problem has been randomly generated. Okay, still running. Okay, we're gonna wait for a while how the program responds. Okay, let me check my uh, okay, my Open VPN is still working. Okay, so it takes quite a long time. Okay, to generate the 10,000 case problem. Okay, over here only took 5 seconds, but now here it took quite a while because it's 10,000. Okay, I guess that this is not the case of 10,000. Should be only 1 million. No, not 10,000. I'm sorry. The problem that we are running is 10 million, but this one is only 1 million. I think 1 million were on constraint. Okay, uh, took a while here for the row gen. Okay, it took around 82 seconds, 1 minute. But look at how fast it solved. Only 3 seconds to solve the problem. But with this one, we add very few constraints. Only 1, 2, 3, 4, 5, 6, 7. Only 7. Okay, certainly, this problem is different than what we solved up here because it's a different random seed. Okay, I didn't control the how they when they use random number generator that they're gonna generate the same random sequence. Okay, to generate the same number for you. Okay, for different problem that you can expect that you can have a different result. But again, okay, if you move this problem, okay, with similar problem here to work on the LP direct solving, if you add this to only just million or 10 million, you may try it on your computer, okay. I'm not going to try to solve it down here because it's going to take so much time, but I guarantee you the response of the direct solving will not be as quick as when you solve with this low generation down here because it's over here we took only 3 seconds. Okay, but as I told you that you cannot be sure that all the problem will be easily solved within 10 additional constraint. Okay, sometimes you may end up having a multi 100 additional constraint. It depends on the type of structure of the problem, and then the problem that we are working on have almost not special structure. It's just direct random generate number. Okay, so it's very hard to be able to identify the structure of the response of the program to this type of problem. Okay, so we're gonna move on here, okay, to look at the column generation. Okay, over here, yes, I think that I did make it right. You remember that? Yeah, LM here, the original is not 10,000. So the response that I get in the first place when I run here, the only 5 seconds to generate a problem. That's the case of 1 million decision variable. And that time it took 10 iteration, right? And that's why it took longer with 8 seconds to solve the problem. Okay. Remember that for the sub problem, okay, it starts with the same size regardless of the capital M is. Okay. So if you start with the same size, keep adding one iteration by iteration, so the time is not really depend on the capital M anymore. But still certainly depend on you. You know why? Because it's gonna affect this by the command number 36 with RCC equal to right hand side minus the left hand side. Okay, B minus A full times X. Okay, so this is a part of LP with too many constraints. Okay, I'm gonna with a similar idea. Okay, we're gonna move on to look at the Matlab code for LP with too many variables. Certainly, this one with different settings. We start with small m and with the large n of 10,000, and the initial number is 50 also, okay. And this one, okay, a through and a sub, very similar terminology and logic to the program, the previous program of LP with too many constraints, okay. And also the min RC iteration also the same also. The only difference is that how to compute the RCC here, okay. And also the difference is that we now uh, add the new element, okay, to the new column here. Is a different parameter. When you add new column, you have to use 2, okay. When you add new rows, okay, this one is only 1, okay. And also this one is C. We add the new row, okay, because C is a column vector, okay. So that's why going back to the attribute of equal to 1, okay. But again, okay, to be able to identify the column vector added, you have to know that when you facing LP with too many variables, you want to find the new coefficient according to the column vector associated to that variable in the original A matrix, the full size of the A matrix, okay. And also you want to identify the location of the cost coefficient instead of the right hand side, okay, for the LP with too many constraints. But this one, for too many variables, you want to identify for the vector C, okay, here, okay. That's what, okay. So it actually start pretty similar with, we solve the initial problem using instead of A sub and B sub, this time we use C sub and A sub, okay, because it's approximate with the number of constraints. We didn't take all the constraints into consideration in the first place. And for the new variable to be added, we need to compute, this one is already to reduce it, the primal reduced cost coefficient. This one we using this one, if you might remember, is this one is Y transpose. According once you return with the lambda value, and lambda belong to the inequalities. So if you have a equation down here, okay, in MATLAB, both inequality and equation, okay, uh, for each constraint, for the inequalities, okay, the return value is lambda dot ineq lin, okay. For the equation, it will be lambda dot, okay, dot eq lin, okay. It will be equation, okay, instead of inequalities, okay. So but in this case we only use the inequalities, okay, because we don't have any equation, okay. And this one is Y transpose time A full, okay. And you can see that why we did in the formula, original formula here, okay, that we study here. This is the cost coefficients, okay, Cn transpose, okay, minus Cb transpose B inverse N, okay. This one we call the reduced cost. But in the program, okay, in the MATLAB program, okay, we use this C, okay. But the lambda down here, we didn't change we didn't add the minus value, okay. The C transpose is the same. But this one you might wonder why we didn't use minus. We didn't use minus sign here because actually let's go back and look at the property of the simplex, the weak and strong duality here. The definition that we come up with, the sign of the lambda value, or the in this case it's a y, okay, the variable y. You can see that the dual variable have to be negative, okay, when the primal solution or decision variable restricted to non-negative, and you are dealing with greater than or equal, okay, greater than or equal. But in your program down here, okay, the linproc logic here, okay, a x, okay, less than or equal. They all deal, the default inequality is all dealing with the case of less than or equal. So the value of lambda here, okay, will automatically become the negative value, as opposed to the case when you have a times x greater than or equal to b. So what I mean is that if you don't need to put the minus sign here for this lambda, okay, because the resulting of this lambda value will become the negative value, and the negative time the original negative value will become the positive value, okay, the positive value. And the reason is this, that because once you have this definition, it costs you to have this one, that okay, certainly your dual variable, okay, is y cb transpose b inverse, okay, but this y have to be restricted to be the negative value, because the original inequalities in the primal become less than or equal with the minimization. So it costs you with this reduced cost coefficient, that okay, beyond the cb transpose b inverse, okay, y need to be the minus sign, okay, because of the inequality setting. So the minus time minus sign become plus sign, okay. Okay, if you can't follow this, you rewind back and listening again and again, you will see the logic behind that. This is the reason why we don't use put the minus sign here, because lambda automatically, once that you solve this, okay, it was restricted to become the negative, okay. So once you have a negative value, add it here, okay, put the negative lambda here, okay, times, okay, the original formula you already have a lambda minus, okay, time minus become plus, okay. So that's why the RCC over here, okay, certainly we need to use to transpose it, okay, back, because this formula is become the row vector, and you transpose it again to become the column vector. And once you get the column vector, you find the minimums, and then you identify the location. And once you know the location, okay, now the data that you're gonna import into your A submetric and C submetric now is belong to, okay, all row in column index, okay. That will be different from row gen, right? From row gen is because belong to row index, okay, for all column, okay. But for too many variable, okay, okay, for all row in the column identified by index, and certainly the C new is belong to C index, and then you can add the value, okay. This one we didn't add m, we add n, right? Okay, the new A sub, okay, we have one more column of A new, okay, and with C sub, okay, we have one more row, okay, because it's already a column vector here with C news, okay. Once you already update this, you keep solving it again and again until you get all positive minimum reduced cost coefficient. Once you be able to identify that your reduced cost coefficients are all greater than or equal to 0, and it's already guaranteed that your current x is the minimum for the whole system, okay, regardless of you didn't put all the constraint to solve, just like the direct solving down here, okay. So this is the logic behind the what we call the LP with too many column here, the MATLAB file here. Okay, we're gonna run some result for you. Okay, as I showed you before that I already ran it. This one. Okay, this one LP too many variable column gen. Okay, and again we working on the problem with the in this slide the 10 million. Okay, 10 million number of decision variable with only 10 constraints. With only 10 constraints. Okay, certainly it took maybe longer time, like 1, 2, 3, 4, 5, 6. Actually you can just type the if you run it, you can type the value to check out that value is the ITR. ITR will count how many times that this do while loop repeat itself, that implying the number of additional variable, in this case for LP with too many variable, but for the file of LP with too many constraints, ITR imply the number of rows added to the original approximated model. Okay, for column gen down here, okay, this one took almost a minute to generate the problem, and then it took maybe 10 uh, around 20, right? This one around approximately around 20 additional variable added, and it took 14 seconds. Certainly it is more than the case of the 3 second here. Okay, that because you know that in this case you add a fewer row. Than as I told you, it doesn't matter whether you have a different size of capital M or N, the small n, in terms of both are large scale. Okay, in either one of them is in the large scale condition. Okay, it's the complexity and the total time consumed will all rely on how many iteration, okay, within the do while loop of the program need to be executed, because in both cases we almost start with a similar problem, like 10 by 50 for row generation, it will be 50 by 10. Okay, row generation 50 by 10, for column gen is 10 by 50. And also we already run, in this case both have a 10 million constraint, and this one is 10 million variable. Okay, so you just cannot count on that whether this small experiment that I show you while running all the three program to you, okay, can lead you to any concrete conclusion. Okay, you have to now you kind of have a tool based on these three programs. You can work it out by by changing the parameter of small m, large n, and small n. Okay, and in this one also small the capital M, the small m, and small n. Okay, so you need to vary this as a factor, and take a look at the parameter of the total computation time. And also you need to check the validity of the results also. One nice thing is that if you be able to use the same random seed, there's some way that to be able to control that. You might put all the program together that you run with the similar problem, okay, to check whether the results fitting each other or not. It means that when you these two, the validity of these two programs, that with the same amount of data, with the same size of data, and same value of all the data. Okay, when you use LP direct solving, or either use row gen or column gen, leading you to the same result. But as I already illustrate to you that the LP solving will be the time consumed will be increasing rapidly, okay, as either M or N, okay, has been increased. Okay, and also you can see that when you use the same problem that having problem with LP direct solving, the constraint row gen and column row gen can lead you to a more efficient way to get the result, and certainly you get maybe not the same optimum solution, but have to be the same objective of your objective function, either in the both in the minimization case and maximization case. Okay, so now I already show you the three program, okay, that we already code and put it in the file in folder lecture 3. Okay, but we going back to the last slide, okay, for this lecture. Okay, okay. Okay, and that would be the homework, and then the nice thing for you to use what we have studied, and what I have given you, both coding and explanation, trying to solve the problem that you looking at your uh, looking at the screen at right now, okay, which is the linear programming with simultaneous too many constraint and variable. Okay, so far both in Excel and in Matlab format. Okay, we only look at the case where you either have too many constraints and very few as compared to the number of decision variable, or you have too many number of decision variable, okay, with a much smaller number of constraints. Okay, but suppose that both of them certainly based on the formula here, okay, the resulting, okay, and the number of constraints should be less than number of decision variable once you already convert all the inequality to equation. Okay, but suppose you did that, okay, either you have both inequality or equation, but you have found that, okay, both m and n are very large, not a very large, both not can either and can be different number, large positive number. Okay, this one can be either equal or not equal. If it's not equal, m should be less than n once you convert it to the equation. Okay, but you're facing the situation that when you have a very large scale LP problem and also with a very dense data. Dense data, what does it mean? It means that you remember that when we using solving the production planning problem, the LP structure have a special structure that I in the program that we code we can use the sparse metric approximation that help us to okay to escalate the limitation of the program to solve a larger model. Okay, but in this case, we will assume that not only m and n are large positive, as the size, I mean the size of the problem. Too many both have a lot of constraint and a lot of number of variables. Okay, such that what we call the A matrix is out of core memory handling. Okay, it means that if you keep increasing the size one day, okay, you don't even have a chance to solve it because you don't have enough memory. But that certainly will be a much harder case than now today with the current of big data technology. Okay, but this is the situation to extend what we have studied so far. That okay, you can think about this problem in both platform of Excel and Matlab. Okay, okay, that you don't have enough memory to even store the problem, so forget about solving the problem. Okay, but you already have a tool here that when LP with too many constraints and too many variable, okay, you already know that in either case you know how to handle it. Can we mix the strategy of both method to solve this problem? Okay, especially we want effectively the same optimal solution with the large problem and also efficiently, just like in either case of too much constraint and too much variable that I have been illustrated to you in both Excel and Matlab form. Okay. Uh, okay, we gonna finish this clip at this now. Okay, and uh, with this question remaining for you. Okay, but we will spend some time, okay, in the next clip trying to okay provide you with the strategy and then but not gonna and we'll show you some illustration how to solve this type of problem, but not I'm not gonna be showing you all the perfect approach to solve or perfect code for you to answer this question because there will be several different strategy to handle this. Okay, so I think that this clip is quite long enough. Okay, we should stop it here. Okay, but in the next clip we will extend the knowledge. Okay, especially in the MATLAB format, but I will recall your Excel format also. Okay, to discuss about the extension how to solve in this case, okay, of LP with simultaneous too many constraint and variable. Okay, from now, okay, let's stop here and see you later.